In this recording, we're going to take up the kinetic theory of gases and work our way to look at how to derive the ideal gas law actually by thinking about the physics of a molecule bouncing around in a box. This takes us into chapter 6. I know we've been in chapter 5 for a very long time through the course, and now we move into chapter 6 where we'll actually talk about gases for the next several videos. So while we were doing StatMech, we actually derived the ideal gas law at one point by thinking about the translational partition function for a particle in a box. And we used that together with some relationships with thermodynamics to get an equation that actually we could show was equivalent to the ideal gas law. What we're going to do in this video is actually somewhat more historically like the way that the gas law was first justified, at least theoretically, okay? And that is, we're going to think about just the classical physics of a molecule bouncing off of walls in a container and use that along with a couple of very simple assumptions to put together a description of an ideal gas. And from that, we'll get ourselves to the gas equation itself. So let's get started. All right, what we're going to think about is this. We're going to have a single molecule bouncing around in a cubic box. So we're just going to make the box be a cube because that's simpler. We'll make the distance between the two walls in any one dimension in the cube be L. Okay, so the width of the cube or the dimension of the cube is just going to be L for purposes of the equations as we start going. All right, if we come over here, you can see that I have a molecule, and in the beginning on the top, before it bounces into the wall, it's moving in the left to right direction on our screen. It's traveling with a velocity Vx, at least that's the x component of its velocity. Okay, so we can ignore the other two directions for now and just say our molecule is about to crash straight into the wall. Okay. When it hits the wall, one of the assumptions we have to make for our gas is that the collisions between the molecules and the walls have to be elastic. Otherwise, the energy of the gas would constantly decrease or increase, and that doesn't seem physically real, right? So after the molecule bounces off the wall, if it hits it coming perpendicular to the wall, then it's just going to turn around and go the other direction. If it's not perpendicular to it, the same thing is still going to happen to the x component of the velocity. So then it's going to have a velocity minus Vx, meaning it's going in the other direction, okay? And so that says our molecule comes in, bounces off, is headed now from right to left across the screen. So the change in velocity for that collision is just written here, and the total change in velocity is just 2Vx because it goes from Vx to minus Vx, and so the net change is 2 times that original Vx. Next, just Newtonian physics. We take the force applied to the wall. The reason we're taking the force applied to the wall, of course, is because pressure is force per unit area. And that's how we're going to work our way towards having things in terms that are what goes in the gas law, is to get to pressure, right? So the force applied to the wall is just ma, where that's mass times acceleration. M is the mass of the particle. A is the acceleration on the particle. And that acceleration, of course, is just the change in velocity with the change in time, right? So we have this dv dt piece here, and we know something about how the velocity is changing because we have the equation up here and the description over here, which says that our particle starts at Vx and goes to minus Vx, right? And so dvx up here is just going to be this 2Vx, right? Because we said that's the change in velocity from the collision is this quantity here. I still have a dt on the bottom. So now I have to figure out what is the increment in time that I should attribute to that collision. And the answer is, if my particle goes back and forth, think about the, look at the picture on the bottom down here. If I look at this one, my particle starts going here, say it bounces off the wall, it comes back this way, bounces off of this wall, comes back across again, eventually it will hit that wall, right? Remembering that we have the box set up so that the length across here is L, then it's going to be true that the time between collisions with one of the walls is just going to be the time it takes the particle to go a distance of 2L, right? Because if it hits this wall here and goes this way, it goes L in that direction, then it has to go L back again the other way before it can hit the wall again. So it'll hit any given wall every time it travels a distance of 2L. So down here, I've put for the increment of time, I've put 2L, which is the distance, divided by Vx, because that's the velocity, right? If I take distance and divide it by velocity, I'm going to get time. So that's my time step for the time that it takes between hitting that wall once and hitting it again. From that equation, I just do, I cancel the 2's and I flip the Vx from the bottom in the denominator up into the top, and I get this last statement over here, which says that the force applied to that wall is just going to be mv squared over L, where the V in there is this x direction velocity that we've been working with. Okay, so keep that result with us, and we come over here. Top equation is just the one we had on the end of the last slide, right? Now we want to take this and get to pressure. Pressure is force per unit area, as I mentioned. The area of the wall is going, the box is a cube, and so it's L in all the dimensions, and so for A, I'm going to replace that with L squared, because the area of any one of the walls of my cube is going to, of course, be the edge length squared. So that says pressure. I start off labeling this as pressure in the x direction. We'll remove that momentarily because pressure is not really a directional quantity. That's going to be just the force over L squared. We know the force from the equation on the top. When I take that one and divide it by L squared, I can work my way towards the version over here, which says it's mv squared, mvx squared over v. That's the pressure exerted by one molecule on that one wall of the box, okay? If I want to have a bunch of molecules, because a one molecule gas doesn't really give me a lot of things I could do, then I'm just going to put in an n to be the total number of particles, all right? Next up, I'm going to take the x subscript off of P because pressure has to be the same in all directions, right? If the pressure is not the same in all directions, then the gas will just be flowing. That's not the situation we want. We want a gas that's just trapped in a box, and so it can't exert more force on the wall on one side of the box than it does on the other, or in one direction and in the other, right? And so that tells me that I can take the x subscript off of there. I put the n in because my equation up above was for one molecule. That gets me here to an equation that says the pressure can be written as being the number of molecules times mv x squared over v. That term that's in there, the Vx squared, where we put the bar over that, when we went to having n molecules, that means we can't just say they all have the exact same velocity, right? That's not physically realistic for a normal gas. And so that Vx squared with a bar over it, that's the average of Vx squared, right? So if I was calculating that for a small sample of molecules, I would find the velocity of each molecule, square that, and then take the average of those squares, okay? It turns out there's a difference between taking the average of the squares and taking the square of the average. We'll talk more about that in a couple of videos from now when we talk about molecular speeds and energies and things like that in more detail. Okay. So this is the equation we have so far for saying our molecules are just bouncing off of that one wall of the container, and we've essentially argued that it should be the same no matter which wall we look at, right? Because it was kind of a random decision when I said I'm going to pick out this wall and say it's the one my molecule is bouncing off of. The average of v squared in the three directions needs to be the same, right? So Vx, average of Vx squared or Vy squared or Vz squared, the three terms over here, those all have to be equal. If they're not, then the entire volume of gas is just moving through space in one direction or another, right? Because that says it's got a net progress somewhere. The average of the actual v squared, where I get out of being one-dimensional and get to a three-dimensional velocity, that needs to be the sum of the averages of the components of the velocity, right? So this middle version of this just says that I have my v squared, where that's just now the actual velocity of the molecule, no matter what direction it's going. That's got to be equal to the sum of the squares of the three components of the velocity there, the sum of the averages of the squares of the three components of the velocity. And since all three of those components need to be identical, that says that the one we've been working with, that is the average square velocity in the x direction, that's got to be the actual average square velocity just divided by 3, okay? And so now I'm going to take that result, I'm going to put that in up here for what is my Vx squared. When I do that, what's going to happen? I'm going to take the x off, and essentially I'm just going to stuff a 3 down in the bottom with the v. So that gets me this equation here, which says I've got the number of molecules times the mass of the particle times the average of v squared all over 3 times the volume. Okay. Be a little bit careful here of the velocity v in the top and the volume v in the bottom in this these couple equations, because those are clearly different parameters. Just multiply both sides of that by v, and I get something here which says that PV is equal to just NMV squared over 3. So that's the equation, that's a result that tells me what PV is equal to. We want, for our ideal gas law, we want to say that PV is equal to nRT, of course, and we're almost there, actually. We know that the average kinetic energy for n molecules is equal to just this quantity here. That just says the average, the energy of a molecule is mv squared over 2, 1/2 mv squared, sort of your classical physics equation for kinetic energy. Our molecules, our ideal gas molecules, we start off thinking about them as just point masses, right? And so that says that they only get translational kinetic energy. So that's the total energy they have. I put in the average of v squared there because I'm going to average over my large collection of molecules. That thing needs to be equal to, just from what I've got up here, if I compare this equation and the one up here, that says they differ essentially by that that factor of 3, right? If I take 3 PV, that's equal to NMV squared. I want NMV squared over 2 here, and so that says that the kinetic energy is equal to 3/2 times pressure times volume. Okay. In order to connect this up with the traditional form of the gas law, we have one last thing to do, and that's to invoke the idea that the translational energy is just 3/2 RT, right? Because each dimension gives us a degree of freedom. Each one of those degrees of freedom can contribute energy of 1/2 RT. Put those together, I get 3/2 RT for the translational energy. And this one says this is the total energy, but the total energy and the translational energy need to be the same thing. So I'm going to take those two equations and equate them, okay? If I did that, let me scoot back here for a second. If I did that, I'm going to say that I have 3/2 times PV equals 3/2 times RT, okay? Which I could scribble that over here. I had 3/2 times PV equals 3/2 times RT, right? The 3/2 obviously can go away. And because I've got R in there, I want to focus on molar quantities for this, right? So R is a per mole entity. If I had a mole of gas, I would have Avogadro's number of molecules. So I can sort of make this equation a little bit spiffier here by putting this subscript m on my volume. That says that the pressure times the molar volume is equal to RT. And what that is the ideal gas law, right? Because the ideal gas law, as you normally write it, when we say PV equals nRT, we just say, well, n is the number of moles, and if n is 1 mole, then V over here is the molar volume, right? So what that equation tells us is we've taken and we've essentially derived our way to the ideal gas law by doing nothing but just sort of first semester physics, thinking about the change in momentum, say, as the particle bounces off the wall, okay? What have we actually assumed along the way? We assumed that the collisions between the molecule and the wall were elastic, because we said the speed didn't change when it bounced off the wall, right? It just reversed direction. We also, without actually thinking about it overtly, we assumed that the molecules were non-interacting point masses because we used the volume of the entire cube as being accessible to all the molecules, for example. And we didn't think about collisions between molecules, because if the molecules don't actually do anything but bounce off of each other elastically, then those collisions make totally no difference, okay? It's important or worth pointing out that the gas law itself was originally derived empirically, right? People started studying gases, most notably air, because, well, there was lots of it around, it was easy to get, and just did experiments that looked at how, say, the pressure and the volume depended on one another, that sort of thing, and gradually put together what we know as the ideal gas law, right? When you take Gen Chem, you often learn about individual pieces of the gas law, right? So you'll say this is Charles's law and Boyle's law, named after people who did sort of the go-to experiments for each actual piece of the thing, right? Much later in the game, the arguments come along that we just used here to say, well, if molecules act in these couple of ways, then we can actually just derive from very simple assumptions the idea that that should be the result. So that's a really great example of how science kind of works, where we take an empirical result and then we do modeling or what have you. We come up with a physical explanation. That physical explanation then leads us to having more insight into other things. And that's in fact how we do science in lots of ways still up through today. Let's see, I put another question in here. So again, you can just stop and take a second. This is really, again, just a throwback to general chemistry. I'm confident that you all learned these things under here. It looks like I have my head floating over one of the words in the question. I tried to rework some of the things that wouldn't happen too much, but it just says a gas is most likely to deviate from ideal behavior under conditions of, and it gives you 4 choices, right? So if you're not immediately sure what that is, again, you can pause and think about it for a second. I will just go to the result and say that when the gas law works best, if you're not sure how to think about this, the really great way to do it is just say, what are the conditions that would make a liquid turn into a gas, right? And the answer is that they are either by raising the temperature or by lowering the pressure. Either one of those things would let you liquefy a gas, right? And so that says D down there is the answer for when a gas wants to be ideal. I just answered the opposite of the question. It's most likely to deviate from the gas law at the opposite of those conditions, which would say at low temperature and high pressure is when it would actually deviate, because those are the conditions where a gas is more likely to liquefy. All right, I apologize for starting to answer the wrong question. All right, lastly, for this one, when we start to think about deviations from ideal behavior, it's really because the assumptions in the gas law begin to break down, right? The 2 non-physical assumptions in the kinetic theory model, and there's a list of postulates in the kinetic theory, but one of them is that a gas has to include a large number of molecules, for example, which is sort of trivially satisfied if you have any measurable amount of gas. But the 2 that are the weakest are one that says the molecules are point masses, and real molecules are not point masses, they take up space. Right? We know that because if we get a solid where the molecules are pressed tightly together, it still takes up volume, right? Its volume doesn't disappear. If you take the gas law, it would say that in the limit of high pressure or low temperature, volume should go away, right? And that can't happen, okay? So the molecules really do have volume. The other one is that molecules do interact with one another during collisions. If they didn't, if there weren't some sort of attractive forces between molecules, then everything would always be a gas, right? We wouldn't be able to make a liquid or a solid or to talk about liquids and solids because we'd be gases, okay? And so those are the things that are the parts where this will break down. The limits we just talked about before, the fact that the gas law breaks down and doesn't work well. If the temperature is too low, we'll see that's because then the forces between molecules begin to matter more because the molecules are moving slower, right? If the pressure is too high, that says the molecules are squeezed tightly together and then the volume that's occupied by the molecules becomes a lot more significant. When we work with models for real gases, they account for these 2 things in one way or another, okay? In the next video, we will take up the idea of a van der Waals gas and do a little bit of work to see how that equation behaves and look at the conditions under and the extent to which it does a better job than the ideal gas law if we're willing to do the extra work to use that equation. Thanks.